Swayam Prabha. Digital India. Educated India.
So, in the last class we discussed about a Markov process. So, Markov process is a subset of a stochastic process, and it has this property that the future state depends only on the current state and no other past. And that kind of property basically allows us to write a joint distribution function for any stochastic process through a recursive transition probabilities. In this class, what I want to do is we will take certain form of the transition probabilities, and then we see whether they follow or whether they obey the Chapman-Kolmogorov equation, which is a kind of a consistency test for a Markov process. Okay, so let us first summarize what we learned in the last class. So, a stochastic process this is defined by a joint probability distribution P of we say like x1 t1, x2 t2, and all the way up to xn tn. Okay, so this probability basically gives me a trajectory of a particular stochastic process as a function of time, where the time is taken discretely as t1, t2, t3 all the way up to some tn. Then we say that for a Markov process, we say that the transition probability of xn at tn okay, the outcome at time tn, the outcome that is xn depends only on the previous time step here, where the state was at t n minus 1. It does not require any information about where the system was at n minus 2, n minus 3, n minus 4 and so on. Okay, and this is what we call it as a Markov property. This, along with a single point distribution, fully describes the Markov process. Okay, so we are saying that once we have this kind of a Markov property, then we can construct this joint distribution function through a product of many transition probabilities. So, if you want to write P of xn tn x minus 1 tn minus 1 all the way up to x1 tn. So, you basically write this as p1 x1 t1 as if this is the initial state specified, and then product of So, with the knowledge of the single point distribution and the transition probability, we can construct this endpoint joint distribution through this recursive relation. Okay, we start with x1 t1, and then we know given x1 t1 what is the probability of finding x2 t2 times given x2 t2 what's the probability of finding x3 t3, and then all the way up to n. So, the knowledge of the transition probability allows us to construct the entire stochastic process. Okay, in this case it's a Markov process. This is what we learned yesterday, and what we are talking about is more of a solution to a Markov process. Okay, this is going to be an analytical function of a particular Markov process. It can be a Brownian motion, it can be some chemical kinetics and other equations. Okay, so now to test whether a given function like this follows Markov process or not, we introduce this concept of Chapman-Kolmogorov equation. And suppose if you take times like t1 greater than less than t2 less than t3, the Kolmogorov equation basically goes as P of x3 t3 given x1 t1 must be equal to the integral of So the Chapman-Kolmogorov equation is written for a 3-point distribution as given x1 t1, what's the probability of finding x3 t3? This is given by an integral over multiplication of two transition probabilities, one that involves from going from x1 to x2 and then from x2 to x3 and then looking at all possible values of x2. Okay. So we are saying that the system is able to go from t1 to t3 via several possible intermediate states. Now, when I substitute the given analytical function for the transition probability in this expression, then this should satisfy. Okay, and this is written if x1, x2, x3, which is a random variable here, is a continuous variable. Suppose if you think about a discrete variable like number of molecules or number of electrons, which are discrete numbers, then this integral is replaced by a summation. Okay, for example, let's say we think about n1 and n2 and n3. These are all discrete random variables at time t1, t2 and t3. The same equation here can be written as P of n3 comma t3 given n1 at t1. This has to be sum over all possible n2 p11 n3 t3 n2 t2 times this equation, they are basically the same. This is a continuous case, this is a discrete case. This is for a discrete Markov process and this is for a continuous Markov process. So when you do the summation here, you have to sum over all possible n2. Whatever allowed, whenever we think about a random variable, we know we also define a range. So this summation is over the range of the random variable n2. Similarly here, this integral is over all the range of possible x2 values. So now what we will do is, we will give some examples of this function, analytical function, and then we will put this through this test and then see whether such a transition probability follows Chapman-Kolmogorov equation or not. Thereby we say whether the given transition probability represents a Markov process or not. Okay. So this can be one possible transition probability, that given x1 t1, the probability of finding x2 t2 has this kind of a Gaussian form. Okay, so now what we want to do is, we want to use this expression here and then integrate over all possible x2 and then see whether we get x3 t. Suppose if I replace x3 with x2 with x3 and t2 with the t3, then I should get the same answer on the left and right hand side. Okay. So first what we will do is, we will write these two functions. This x2, x1, t1, t2 is already given. So now we will write p of 1 by 1 x3 t3 x2 t2 . So now we want to multiply these two quantities and then integrate over all possible x2. Okay, so you can go ahead and do this, but in my notes you will see that I have done that way. But for this class, what we'll do is we'll make a little bit of an assumption. We will say that T1 is 0 and T2 is some delta and T3 is some 2 delta. This is just to make the number of terms a little simple. So the choice of T1, T2, T3 has to follow certain order. It has to be either increasing or decreasing. We are not saying anything about the interval in these equations. Okay, T1 can be anything, T2 can be anything, T3 can be anything, provided that T1 is less than T2 and T2 is less than T3. For the proof of this theorem, this consistency test, I would like to simplify so that the times are equally spaced, so that this equation becomes a little easy to solve. Okay, so now if I choose this, we again maintain that at the T1 you have x1 and at T2 you have x2 and T3 at x3. Okay, so we can rewrite these equations with this choice of time intervals. So I have P11, or maybe we can directly substitute in the equation here. So you can see that when I make this choice, this T2 minus T1 here becomes delta, and this also becomes delta. Okay, T2 minus T1. Similarly, T3 minus T2 is also delta. Okay. So now we write that T1 is 0, T3 is 2 delta, integral over all dx2, the product of these two. So when I multiply these two, I get 1 by 2 pi delta that comes out of the integral. Then I have only these two terms. So both of these terms are functions of x2, so we keep it inside. So now let's expand these terms. So we have x3 x2 minus x1 whole squared plus x3 minus x2 whole squared so x1 okay, Okay, let's write first the x2 term, x2 square. There is one x2 here and another x2 here, so we have 2 x2 square minus x2 into x1 plus x3 plus x1 square plus x3 square. And then this term is divided by 2 delta. So this exponential term that we have here is basically the exponential of minus one by delta x2 square minus x2 x3 Okay, just check if everything's okay. Oh, there is a delta here. Okay. So what we are saying is that when I try to expand the product of the two exponential, it basically comes in the quadratic form of x2 square. Okay. This is a variable that I want to integrate. So basically, I'm writing this by opening up this terms. I'm able to show there is a quadratic equation that is coming out in terms of x2. In this case, x1 and x3 are constant because we are only integrating over x2. Okay. So that's why we write this in terms of the quadratic equation in terms of x2. Then if you see this quadratic form, I can write simply as ax square plus bx plus c, where a, b, c are nothing but, if you match this equation with this, you will see that a is nothing but 1 by delta and b is the linear term, that is minus x1 plus x3 by delta, and the last term, that is the constant c, is this. Okay, x1 square plus x3 square by 2 delta. Okay, so now if I look at this alone, we have an analytical result for that. So if you have integral from minus infinity to plus infinity, e power minus ax square plus bx plus c dx is given by square root of pi by a e power b square by 4a minus c. Okay. So now all we need to do is we want to integrate this, okay, and that basically is given by square root of pi by a. So you have to substitute for a from here, and this term b square by 4c minus a from here, and that basically is the integral value. So first we will get this exponential term, and then we'll continue. So we want to find b square by 4a minus c. So b square is x1 plus x3 whole squared by delta square, that is b square, 1 by 4a, 1 by 4, 1 by delta minus c, that is this. So this delta goes up and then cancels by 1, so you have only a delta in the denominator, actually 4 delta in the denominator. And now you can open this up, you get x1 square plus x3 square plus 2x1 x3 minus x1 square by 2 delta minus x3 square by 2 delta. So from here you will get minus x1 square by 2 delta, sorry, by 4 delta minus x3 square by 4 delta plus 2 x1 x3 by 4 delta. So this entire term b square by 4a by minus c basically becomes simply minus 1 by 4d x3 minus x1 whole squared. And this term square root of pi by a is nothing but square root of pi delta, because a is just only 1 by delta. So when I substitute all these things here, we see that we get square root of pi delta. There is one more term, we have to also include this one. So there is a prefactor of 2 pi delta. This prefactor is 1 by 2 pi delta. Then this square root of pi by a is square root of pi delta. Then you have exponential of that term, that is minus x3 minus x1 whole squared by 4d. So the prefactor term becomes 1 by square root of 4 pi d, and here you have exponential of minus x3 minus x1 whole squared by 4d. Now what is this we are looking at? We are looking at p of x3 comma 2 delta t delta given x1 comma 0. So we are actually taking a time interval of 2 delta. Okay, so we can rewrite this 2 times 2 pi 2 delta, and here x3 minus x1 whole squared by 2 times 2 delta. And this is what you would get if you were to apply the given transition probability from 0 to 2 delta. Okay. So therefore, we show that this given transition probability satisfies the Chapman-Kolmogorov equation. Therefore, this transition probability can represent a Markov process. Okay. Even though I have shown this with respect to 0, delta, 2 delta, you can even take T1, T2, T3. You can do that. It's going to be a little bit more messy, more terms to handle, but we can still prove this. Now, this Markov property, because of this requirement, there are only few analytical functions that satisfy this. Okay. With regard to the, let's say, if we look at discrete case, discrete state variables, there are a bunch of transition probabilities that follows. Okay, I'll give you a list, and this may be a homework for you to kind of test the satisfaction of this Chapman-Kolmogorov equations. So we already looked at a Gaussian form for a transition probability, and another possibility is this. The second one. So do you recognize this form, this function? Have you seen this before anywhere? You might have come across in your probability course or any other math course. Sorry? Inverse functions. No. It is a kind of a probability distribution. This is called Cauchy distribution. Okay. It is like a bell-shaped curve, like Gaussian, but it has a very long tail. Okay, only decaying at the infinity range. So it turns out that the transition probability written in the form of a Cauchy distribution also follows or also satisfies Chapman-Kolmogorov equations. Okay, so here again we are treating x here as a continuous variable. What about this? Do you recognize this? It's a Poisson random variable, or we are written in terms of Poisson process because there's a time involved. Okay, so here n1 and n2 are discrete variables. Okay, and this is the Poisson process. N can only take values from 0, 1, 2, 3 onwards, and T2 is greater than T1. N can only increase in this case. Okay. So under these conditions, this also follows a Markov process or satisfies Chapman-Kolmogorov equations. What about this process? Binomial. And apparently this also follows Chapman-Kolmogorov equations. So what we are trying to say here is that we are not talking about what process, physical process, and how we are modeling it and how we are arriving at the solution. We are not really saying that yet. But suppose you have done all that. There is a physical process. You have formulated the problem. You have obtained the solution, and the solution has this form. Okay. Then whether the arrived solution follows a Markov process or not is what we are testing. But all of them, all the 4 examples I've showed, is actually coming from a physical example. The first one I showed is basically a Gaussian process for a Brownian particle's position, okay, treated as a random variable. Okay, it's basically a diffusion problem. This one also has a Brownian-like fashion, but under certain external field and external conditions. This one basically mimics a forward walking of an enzyme on a microtubule. Okay, if you take a random walk, it's called one-sided random walk. Okay, so the Brownian motion is a it has a probability of walking forward and backward equal probability, right? Suppose if you break the symmetry, you say the step can only be taken forward. Okay, so that's called one-sided random walk. The one-sided random walk basically gives a solution of this form, which we call it as a Poisson process. This is very widely used in this on the kinetics of protein walking on a microtubule and things like that. What about this one? Anyone can guess this? What do you think this represents? Any physical process that it follows a chemical kinetics exactly. Okay, so when you have A giving rise to some B, a first order kinetic, this basically tell you how many molecules will be there as a function of time, starting with certain number. Okay, so all the solutions are actually obtained by setting up a problem and solving it, arrive at the solution. We are going a little bit backward. We are saying, okay, if this is the form of the solution, whether they qualify to represent the Markov process or not. Okay, subsequent to this, all we want to do is we wanted to kind of set up a kind of a differential equation for the transition probability and apply the differential equation for many of the process, and then you solve analytically or numerically, and that's then we have so many options to look at. Okay, so that's how we are going to evolve. So next to this, what we will do is we will kind of distinguish ourselves into 2 mode. One that follows continuous Markov process, where the random variable is a continuous process, a continuous variable. On the other hand, there could be a random variable where the variable is a discrete, like number of molecules in that case, or the number of steps taken. Okay, these are examples of discrete Markov process. So we'll distinguish ourselves into this continuous and discrete, and then we'll deal with each of them separately and look at more such problems. Okay, so that is the follow plan for this. So we have a few more minutes. Please go through your notes of today's discussion and let me know if you have any questions. Or you can also try doing this, take one of this and try to solve by yourself.